At one point we listed various strengthening mechanisms, in particular 4 strengthening mechanisms which can be used to strengthen a crystalline solid which is deforming plastically with aid of dislocations. Strain hardening is one such phenomenon. So, let us look at what happens in strain hardening. So, let us have a stress strain diagram. We have seen this, and we see that if you apply stress and trace the stress strain of some object, initially it deforms elastically, but then and it remains a straight line in the elastic part, but then the curve becomes non-linear and the plastic deformation begins, and we continue the plastic deformation. In a normal test, we will continue the plastic deformation right up to the fracture point, but let us do a different kind of test where, let me note this point, this is the yield stress. So, we deform the material beyond yield stress. So, there is plastic deformation in it, but we stop the test much before fracture, and then we unload the specimen. The unloading curve is found to be parallel so we loaded and then we unloaded, and this much, as we have seen before also, this much of plastic strain remains in the material. Residual plastic strain remains in the material. Now, so what we have done, we started with, remember, our dog bone kind of specimen for tensile test. So, we were pulling this under tension and we were generating this curve. Now, although the sample has plastically deformed, so it is elongated. So, let me try to draw the deformed sample. So, it is slightly longer now, and maybe diameter is also a little bit reduced, but otherwise the sample is still intact. So, this is the unloaded specimen. So, let me switch off the stress now. So, after plastic deformation, I have an unloaded specimen which is little longer and maybe a little smaller in diameter than the original specimen. Now, suppose since this specimen is still existing, we have not lost it, it has not broken. Suppose we repeat the tensile test on this, what will happen? So, let me create a new axis for our repeated tensile test. So, we are shifting the origin. So, now I am taking the 0 of the strain here, the new 0 of the strain here, and we are loading, we are retesting the loaded sample, or we are retesting the strained sample. Strained or deformed sample. So, what we will see, what we will find, that is the question. In particular, in terms of the yield stress, will it show the same yield stress sigma y, or will the yield stress be higher, or will it be lower? So, that is the question. In a retest, is the deformed specimen weaker than the original specimen? So, it will show a lower yield stress, or it is say yield stress is some sort of property which does not affect by deformation and remains the same. So, yield stress remains the same in the deformed and undeformed specimen, or the final answer that the yield stress is actually larger. You have deformed the material, and due to deformation the material has become stronger. Which of these three options will you choose? Again, we have seen again and again in this particularly in this plastic deformation chapter, that such questions cannot be answered philosophically. You have to actually do the experiment and find the answer. So, we propose the question to the nature. So, we actually do the test again. So, in our retest, what we find, first thing we find that the slope of the stress strain curve does not change. So, the modulus is exactly the same. So, there is no effect of straining or no effect of deformation on the modulus. However, the curve does not show a deviation from linearity, or it does not undergo plastic deformation at a stress lower than the original yield stress. So, it continues up to the original yield stress, but it does not stop there. It continues further beyond up to the point where you have started unloading. So, it sort of remembers its point from which you had unloaded it. So, that point becomes your new yield stress, and then it continues its plastic deformation. So, which means that after deformation, when the test is done on a plastically deformed specimen, the deformed specimen has a higher yield stress than the undeformed specimen. Let us write this important conclusion, that sigma y deformed is greater than sigma y undeformed. And this effect, this is the phenomenon which has been termed strain hardening. The question is why it is happening, we will look at that, but at the moment, at the level of definition or at the level of observation, what we see is that if a material is plastically deformed and then tested in a uniaxial tensile test, it will show a higher yield stress than an undeformed specimen. So, in a way, this plastic strain, what was the difference between the red curve and the blue curve? The blue curve was originally tested and had no plastic strain, whereas the red curve has an inbuilt, this much amount of plastic strain is already there in this, and that is why this is called strain hardening. In engineering, it is also called sometimes work hardening, because process of plastic deformation engineers call cold working or working. So, it is also called work hardening. So, strain hardening and work hardening are synonyms. Now, let us think of it, since plastic deformation is involved, dislocations are involved. So, let us think of it in terms of dislocations. So, we have already seen that plastic deformation increases the amount of dislocation in a material, increases the dislocation density. Dislocation density. But we have also seen, and that is how the dislocation was proposed in the literature of science, as a mechanism or as a device by which you can deform the material at much lower stress than the real crystal, than the ideal or perfect crystal. So, we have also seen that dislocation weakens the crystal. So, if you put 1 and 2 together, the normal conclusion will be dislocation weakens the crystal, plastic deformation is generating more dislocation density. So, deformed crystal should be weaker. But we have seen that this is not true, experimentally not true. This conclusion is incorrect. Experimentally, deformed crystal is stronger. That is what we call strain hardening. So, then how do we resolve this conundrum, this problem, that dislocation is weakening the crystal, we are generating more dislocation during plastic deformation, still crystal instead of weakening is strengthening. This conundrum is explained by what we call dislocation interaction. So, what really happens, that when plastic deformation starts generating more and more dislocation, one dislocation comes in the way of other. So, and they start interfering with each other's motion, making each other's motion more difficult. So, there is an interference, by other dislocations. For motion of a given dislocation. And this will, of course, if the dislocation motion is becoming difficult, so the yield stress or the stress required to move them will go up and the strengthening will happen. So, difficulty in motion which will lead to strengthening. We are talking in a very general term. In the next video, we will try to see in a little bit more detailed fashion what do we mean by such interfering dislocation interaction.